they like industrial process questions because it's obviously a very important kind of context to test out your understanding of rates of reaction and equilibria and atom economy and all these kind of things. So good to practice questions like this because you're very likely to get the same ideas coming up. Okay, so this is the reaction that question 3 is based on, and the first couple of questions are asking you to use your Le Chatelier skills. Okay, so equilibrium questions are likely to be along the lines of what happens to this equilibrium when you make whatever change it asks you about. So be absolutely clear you've got Le Chatelier nailed down. What he says is that if you've got a system that's in equilibrium and then you change the conditions in some way, that the equilibrium will shift in whatever direction opposes that change. So in other words, if you increase the temperature, it will shift in the direction that tries to decrease it again. If you decrease the pressure, it will shift in the direction that tries to increase it again. And that's all you have to do is to figure out how that will actually occur in practice. So first of all, it wants to know what happens if you increase the pressure. So you look at the reaction and you remember that each mole of gas contributes the same amount to the pressure. It doesn't matter what gas it is. So all you have to look at is the total number of moles of gas on each side of the equation. So in this case you've got 2 moles of gas on the left, but 4 moles of gas on the right. So if you increase the pressure, Le Chatelier says it will shift in the direction that tries to decrease it again to oppose the change, and you can see that will be to the left because that decreases the moles of gas, therefore decreases the pressure and opposes the change. Okay, it's very important that you set that out fully in your answer to make sure you get the marks. So you have to say equilibrium shifts to the left because there are fewer moles of gas on the left, and therefore that will oppose the increase in pressure. Make sure you use that language of opposing the change or minimizing the change, but not cancelling out, because it doesn't completely cancel it out, it just doesn't make it as big as it would otherwise be. Okay, but it's minimize or oppose, those are the sort of words to use. Also with questions like that, make sure you read it carefully, because sometimes it says something more specific like what happens to the amount of methane or what happens to the amount of carbon monoxide. And again, it's important you answer that question specifically. But here it didn't, it just said what happens to the equilibrium, and they like you to use that language of shifting to the left if it moves that way, or shifting to the right if it moves that way. Okay, so part B, along similar lines, what happens if you increase the temperature? Well, the information you're given that relates to that is that delta H for this reaction is equal to plus 210 kilojoules per mole. When you have a reversible reaction like this, remember that the value for delta H that they quote is the value for the forward direction going from left to right, and that the value for the back reaction will therefore be minus that. So if it's plus 210 going forwards, it's minus 210 going backwards. And it's absolutely crucial you remember what those signs mean. Okay, so plus 210 is endothermic, positive is endothermic, and that means it takes heat away going in the forward direction. If you go in the back direction, it's negative, that's exothermic, and that means it gives heat out. So the forward direction takes heat away, will tend to cool the system down. The backward direction is exothermic, gives heat out, will tend to warm it up. So with those ideas, the question is what happens if you increase the temperature, and the answer is, well, it will shift in the direction that tries to decrease the temperature, and that's the forward direction. So it will shift to the right because that's the endothermic direction, so it will take heat away and oppose the change. Okay, now the next little bit is asking you to comment on the actual conditions used, and then specifically on why do you think you use a pressure of 30 atmospheres. So this is not necessarily going to be to do with the equilibrium, and in fact we predicted in part A that an increase in pressure, and obviously 30 atmospheres is a reasonably high pressure, that would actually shift the equilibrium to the left, which is not what you want to do, because you want to make hydrogen, so it will decrease the amount of hydrogen produced at equilibrium. So you have to think, well, why would they do it then? You know, they're not stupid, there must be a good reason for it. And The next thing always to think about is, well, what about the rate of reaction? Because that's always going to be a consideration, that you want to make your product quickly so you can make as much as possible in a reasonable time. And of course, increasing the pressure increases the rate of reaction, because the molecules are closer together, so they collide more frequently, and that increases the rate. So I think what you want to suggest in this case is that you use an elevated pressure, 30 atmospheres, because that will increase the rate of reaction so that hydrogen is produced more quickly, but that there has to be a compromise. They love you to use that word compromise, to emphasize that you understand that you have to think about several factors and that they may not all benefit from the same change. So there has to be a compromise. You don't want the pressure to be too high, because if it were, the equilibrium would shift too far to the left and the yield of hydrogen would be too low. It would also be true, of course, that if the pressure were too high, it might become dangerous, and it would become very expensive to set up the equipment to tolerate the pressures. So there are lots of things you could talk about. It was only one mark here, so you didn't need all of that. But it's important, in a question where you might easily have had 3 or 4 marks, to be able to explore that fully. Okay, so you think about equilibrium. High pressure is not favourable because it shifts it to the left, but that must be offset against the fact that it increases the rate by going to higher pressure, so you produce the hydrogen more quickly, so you establish a compromise between the two, and you can bring in safety and cost as well if you want to. Okay, so now it's time to bring in the Boltzmann distribution, and increasingly they're quite keen for you to draw out the distribution yourself. So this is an important thing to practice. So first of all, you've got to remember what goes on each axis. And the answer is, along the bottom, you just need to write energy. You sometimes see it written as kinetic energy or molecular energy, and that would be okay, but energy is all you need. Along this axis, it's the number of molecules. Okay, so what we're plotting is a distribution of how many molecules there are at each energy level in the system, and you have to be able to sketch the shape of the curve, and you will get judged on the key features of the curve. So the first thing is it has to start at the origin. Okay, in other words, that there are no molecules with 0 energy, and then it rises up from there to a peak like this, and it comes down asymmetrically. So it doesn't slam straight back down to make like a bell curve. It comes down more gradually, sort of like this. That's kind of a horrible shape, but you get the general idea, that it comes down rather gradually towards the axis like that. And that's the sort of shape that you're aiming to draw. Okay. And then it says, okay, we've got to explain how a nickel catalyst increases the rate. So if you remember your definition of a catalyst, it's a substance which increases the rate of reaction without itself being used up, and that it does that by providing an alternative reaction pathway with a lower activation energy, and it's that last bit that's the key thing. So when you put a catalyst in, it doesn't change the Boltzmann distribution. That's incredibly important. So the curve is not altered by having the catalyst there. What changes is the amount of energy, the minimum amount of energy the particles must have to have in order to react, which is what the activation energy is. So what we're saying is that without the catalyst there would be some kind of cut-off energy there, which is the normal activation energy. And the idea is, remember, that only a small proportion of molecules represented by that area there have got sufficient energy to react when they collide. All the rest of them, represented by this big area here, when they hit each other, they do it too gently and they simply bounce off and they can't break bonds and react. So the idea of a catalyst is that it gives you a new activation energy. So on your diagram you label, this is the new activation energy with the catalyst, and it's at a lower value. And you can see the consequence of that is that you now have this much bigger area representing a much bigger population with enough energy to react when they collide. Okay, so that's what you need to mark on the diagram, and then you just need a few words to make sense of that, that the catalyst lowers the activation energy of the reaction, or better, provides a new reaction pathway with a lower activation energy. And the consequence is that a bigger population of molecules now have enough energy to react when they collide, and therefore successful collisions occur more often and the reaction goes faster. Okay, so part D is a percentage yield question, and it's perhaps slightly trickier than most of those kind of questions that you'll have practiced, and therefore it's a good one to make sure you can get to grips with. Okay, so the first thing is to notice that the data you're given are masses, and your instinct, hopefully by now, is that in chemistry calculations, usually what you have to do with masses first is turn them into moles, and that's going to be the key thing. So we're starting off with 200 tons of methane, it tells us. Now some of you know, if you're comfortable with mathematical ideas, you might have thought to yourself, yeah, I can pretend that's grams and it'll all come out in the wash and things like that. And that's great if you can do that kind of thing. But if you're not confident about that, just work with the numbers, don't try and do anything clever, and you know, it may be more cumbersome, but it will work out. So let's just stick with the 200 tons and think, right, that's 200 times 10 to the 6 grams. It tells you that 1 ton is 10 to the 6 grams, so that's easy. You can convert that to standard form if you want and say 2.00 times 10 to the 8, but you don't have to. It will all work out, so let's just stick with that for the moment. And then you remember that moles equals mass over mR, which is equal to 200 times 10 to the 6 divided by 16.0, which is equal to 12.5 times 10 to the 6 moles of methane. Now the question is, what's that number useful for? And the point is that that's going to enable us to figure out our theoretical yield, right? Because the equation tells you that in principle, in a perfect world, each 1 mole of methane will end up giving you 3 moles of hydrogen. So our theoretical yield of hydrogen is going to be 3 times the number of moles of methane. Okay, so what we write down there is that our theoretical moles of hydrogen. Remember, that means if everything were perfect, you know, if the reaction went all the way over to the right and you didn't lose anything along the way, you'd get 3 times as many moles of hydrogen as you had of methane. So that will be 3 times 12.5 times 10 to the 6, which is 37.5 times 10 to the 6 moles of H2. On the other hand, it tells us that what we actually got was less than that, and if you come up with a number which isn't less than that, it means you probably messed it up. But if we calculate the actual moles of hydrogen, it tells us that we had, what's the number? Can't see it now. 68.4 tons, yeah, 68.4 tons of hydrogen are actually produced. So again, we calculate moles is mass over mR for that one, which is 68.4 times 10 to the 6 divided by just 2 for hydrogen, because it's H2. So you just divide by 2, which comes to 34.2 times 10 to the 6 moles of H2. And that's our actual number of moles. Okay, so we've got these two numbers. A theoretical number of moles, which is bigger, as it should be, than the actual number of moles. Okay, and then you just have to remember the definition of percentage yield, which we'll just write up here, that the percentage yield is equal to the actual moles of product produced divided by the theoretical moles. And obviously you have to learn this definition. This isn't an easy subject like physics where you get a formula sheet. You actually have to know this. Okay, percentage yield is actual moles divided by theoretical moles times 100, which is 34.2 divided by 37.5 times 100, which works out as 91.2%. Okay, so that's your answer that you wanted. 3 marks for that. So it was important to show your working, get the individual numbers of moles, write those down, because that's what the individual marks were for the theoretical yield of hydrogen in moles, for the actual yield of hydrogen in moles, and then the 3rd mark for doing this calculation to get the 91.2%. Show you're working clearly in all your calculations, but especially obviously when it's more than 1 mark, so that you've got that insurance policy against sort of small errors creeping in. Okay, so the last part of this question is moving on to the idea that although this reaction we've said is a method for producing hydrogen industrially, that it's advantageous to do something useful with the carbon monoxide as well, and obviously that makes it a more efficient process if both of the products are useful. And it suggests that we can do that by turning the carbon monoxide into into methanol by reaction with hydrogen, and first of all it just wants a reaction equation for that. So we've got carbon monoxide plus hydrogen gives you methanol, which it doesn't give you the formula for, so you have to remember that methanol is the 1 carbon alcohol, which is CH3OH, and then it's simply a very trivial balancing exercise. So you can see 1 carbon, 1 oxygen, so that's taken care of. 4 hydrogens on the right, so 2H2 is all you need to do to balance it. Okay, then it wants 2 reasons why it's important to use the carbon monoxide to make methanol. So there are various relevant things you can say about that. One is that carbon monoxide, remember, is a very toxic gas, and therefore we have to do something with it. We can't just release it into the environment, so we need to do something to turn it into a safe material, and that will deal with that problem. So that's one point. The second is that you can talk about atom economy. So remember, atom economy is equal to the MR of the useful product divided by the total MR of all of the product times 100. And the idea is that you want to maximize that, because by doing that you're maximizing the proportion of the mass of stuff you put into the reaction that ends up being useful. And you can see that if you can end up using both the carbon monoxide and the hydrogen, in principle you could have 100% atom economy. So saying improving the atom economy in order to make more efficient use of the resources that went into the reaction would be another good and important reason for turning carbon monoxide into methanol. Finally, you could also mention that obviously methanol is a useful product, and you should know that methanol is used as one of the components for making unleaded petrol, so it's important as a fuel. It's also used in some solvents, but the fuel is probably the most important use. Okay, and then finally it wants to know about how hydrogen is used in the manufacture of margarine. Again, this is just one of those things that you need to know. So you will remember, hopefully, the alkene reaction. So for ethene, for example, you know that that can react with hydrogen to produce ethane as one of those alkene addition reactions, like that. And what you need to know is that the same reaction can be carried out on unsaturated vegetable oils to increase the level of saturation, and that's what you do when you make margarine. So you take vegetable oils containing these carbon-carbon double bonds. The simple way to say that is unsaturated vegetable oils. You treat them with hydrogen in the presence of a nickel catalyst, and you have to specify that. You need to know that this hydrogenation requires a nickel catalyst. So you take unsaturated vegetable oils, react with hydrogen, presence of a nickel catalyst, and it increases the level of saturation, and that basically makes them more solid, and that's what margarine is. Okay, and that's it for question 3.